All right, welcome back to your favorite calculus class, you guys. We're going to take a look at the first derivative test. So we're going to use the derivative to tell us if a function is increasing, decreasing, or constant. And just a little vocabulary. If you ever hear the word that a function is monotonic on an interval, then that just means that it's increasing on that interval or decreasing on that interval. Monotonic, okay? So formally, it's increasing, meaning as x increases, y increases. Or if you want to be a little more technical about it, if x1 is less than x2, then f of x1 would be less than f of x2. So for example, if you look at this graph over here, hopefully you can see that if I pick 2 points, here's x1, here's x2, can you see how that y value is lower than that y value, right? So we would be increasing anytime it's going up and to the right. And so I'm going to outline that it's increasing there in blue, right? So in this case, we would be increasing from a -1 x value up until 0. Again, we're just reviewing some pre-calculus here. When we're talking about increasing, decreasing, or constant intervals, the intervals are always open-ended. Okay, always open-ended is how we're going to describe that. And then if you notice, there's another area where it goes up and to the right here in blue that I outlined as well. And that's from an x value of 1 to infinity. Right? We name it in terms of the x intervals. So if you were to name where this is decreasing, where would this thing be decreasing? I'm going to highlight here. Let's do it in red, the interval where we are decreasing. So we're decreasing when we're going down to the right, decreasing over here as well, going down to the right. The blue ones were where we were increasing up and to the right. So the red ones are where we're decreasing. So notice it's coming from, negative infinity up until that x value right there of -1. All right, so negative infinity up until an x value of -1, and then from this 0 up until 1. X value is 0 up until 1. All right. And then where are we? Where do we have a relative minimum? Relative minimum. So lowest point in an area. So yeah, with the relative minimums, you can see that, if I cut this off, here's the bottom of a valley right there and right there. So we have a relative minimum of -1. It occurs at both -1 and at 1. Or if you want to name it in terms of, you could name it as the coordinates. You have as an ordered pair, -1, -1, and the ordered pair 1, -1 is another way you could name those local minimums. And then we have a relative max right there at 0, 0, relative max of 0, and it occurs at x being 0. Or if you want to name it as a coordinate, just the point 0, 0. Now, how about absolute minimum? Do we have an absolute minimum here? Do we have a lowest point? Yeah, we do, exactly. It's -1. You see that? Oops, -1. Both of those -1s right there are our lowest points. Both of those. You see how I hit at both of those, which we already named as local minimums or relative minimums. So the relative minimums here are actually absolute minimums. So the absolute minimum is -1. It occurs at -1 and 1, right? Do you have a highest value? Is there an absolute max? Yeah, definitely not. These things just keep going up. Absolutely correct. There is no absolute max. You only had a local max or a relative max, right? Well, here, we were able to read values off the graph, right, as mentioned in the text there. But what if we didn't have a graph given? Like, where does calculus come into play with this? Well, as we discussed last time, we know at critical points where the derivative is 0 or the derivative is undefined, that's where we're going to have our local mins and maxes, potentially absolute as well, right? Just depending on what the graph looks like or endpoints and so on. So at the critical points, we'll have those extrema, right? But what about where we're increasing and decreasing? Well, let me outline this part here in blue where we're increasing from -1 to 0. Can you see how if I took any derivative at any point on there, let me take that derivative at that point in orange. You see how the slope of the tangent is positive right there? Or maybe I take it up here. The slope of the tangent is positive right there. On any point within the interval from -1 to 0, the derivative will be positive. The slope of the tangent will be positive, okay? So the first derivative test, that's where this first derivative test will come into play. It's going to tell us where we're increasing and decreasing. So let me take this part where we're decreasing and going down to the right. That's not very good. Down to the right, okay? If I take the derivative anywhere on that interval, like let me take the derivative at that red point, now my slope is negative. You see how the slope of that red line would be negative? Let me take it at a different point on that interval. The slope of the tangent there is negative. Okay? So how do we do this when we got no graph given with our calculus? Right? Well, what we're going to do is we're going to find our critical numbers, number one. So number one, find our critical numbers to determine our intervals that we're going to test in. And then number two, we're going to say, well, is the derivative positive or negative within those intervals? That'll tell us if we're increasing or decreasing. Right? So and then make the conclusions off of that. So let's look at another graph here, and let's talk about these for a minute. Where are our critical points? Well, here's where here's where the derivative is 0. So C1's a critical point, C2's a critical point, C3's a critical point, C4 is a critical point, and C5 is a critical point because your derivative is 0 or the derivative is undefined at all those spots. And the original function is defined there, right? And so you're going to have either local maxes or potentially local maxes or local mins. Now in between that area, right? And I should put in, here's our endpoints. Notice that this endpoint is an absolute minimum. This endpoint over here is just a local minimum, okay? Now let's go in between them. Between A and C1, I'm going to outline it, see how it's increasing. So the first derivative is positive, so we'd be increasing. Where else is the first derivative positive? Over here. All those slope of the tangent lines right there would be increasing. And here's another spot in green where we're increasing. All those spots were increasing. The derivative is positive. And then the derivative is negative, right? Then we're decreasing. Derivative would be negative. All the slope of the tangent lines there, derivative is negative. And finally here, derivative is negative. Okay? So let's do it now with the calculus and run through it. Okay? So we have this polynomial, x to the fourth minus 2x squared. f of x equals x to the fourth minus 2x squared. Number one, let's find our critical points. So our derivative here would be 4x to the third minus 4x. Where is the derivative equal to 0? Zero, 1, and negative 1 are critical points, right? There's nowhere where the derivative is undefined, right? It's just where the derivative is 0. So that's going to be on our testing interval, those critical points. So number 2, let's do this first derivative test. So I'm going to do the interval, because I don't know what this graph looks like right now. So negative 1, 0, and 1. I'm going to put on my testing interval. You know what? Let me do this down here and make a little bit more room. So here's my first derivative test. Negative 1, 0, and 1. And so I know at those points I potentially would have some local or relative extrema, possibly even absolute, right? But we need to test in between there and find out if the derivative is positive or not. So what I'm going to do is I'm going to test something to the left of negative 2, something to the left of negative 1, like negative 2. So here's my first derivative. F prime of x was 4x times x minus 1 times x plus 1. I'm going to plug in negative 2 and see what the slope of the tangent line ends up being. And so I got negative 8 times negative 3 times negative 1. So it looks like I got negative 24 when I plug in negative 2. So f prime of negative 2 is negative. It's negative, which means the original function must be decreasing up until negative 1. The original function, right? If the slope of the tangent lines on the interval from negative infinity up to negative 1 is f prime is negative, the original function is decreasing. Now I'm going to test between negative 1 and 0, like, how about let's throw in negative a half, right? So f prime of negative a half. So I throw in negative a half. 4 times negative a half minus 1, negative a half plus 1. So I got negative 2 times negative 3 halves times a positive 1 half. So it looks like I got 3/4. Point is it negative or positive? It's positive. The derivative is positive. That means the original function increases between negative 1 and 0. The original function increases between negative 1 and 0. Now we're going to test something between 0 and 1. So how about test a half into the derivative, f prime of a half. So 4 times a half minus 1, a half plus 1. So when I plug a half in, I get a positive 2, I got a negative a half, I got a positive 3 halves. So a positive times a negative times a positive is a negative number. So f prime of a half is negative. So that means the original function is decreasing between 0 and 1. And finally, I'm going to go ahead and plug in something to the right of 1. How about, let's pick 2 this time. So f prime of 2. So I got 4 times 2, 2 minus 1, 2 plus 1. So I got 8 times 1 times 3. So this is positive. F prime of 2 is positive. The original function must increase The original function then increases after 1. Okay? So let's go ahead and name this, or let's fill this in. What were our critical points? Our critical points were -1, 0, and 1. Where is the function increasing in green? Between -1 and 0, and I know it's increasing after 1. Where is the function decreasing in red? Well, from -infinity up to -1, and then the original function is decreasing between 0 and 1. Again, our first derivative tells us about the behavior of the original function, right? And then what about relative mins or maxes? Well, if the function decreases until -1, right, the original function decreases until -1, and then after -1 until 0, it increases. So it increases, let's say to here, until 0. And then I'm going to try and draw this. And then we decrease again. I don't know how accurate this is, until 1. And then I increase again after that, right? Then hopefully you can see you've got a relative min right there. If I decrease and then increase, I'm going to have a relative min. I don't know if it's an absolute or not, but I do have a relative min right there. So relative min at the points at x being -1, which is the point -1, and I would have to plug it in, f of -1. Plug into original, right? So that would be, actually, if I plug -1 in, that would be -1. That's what it spits out. So we plug that into the original function. We will also have a relative min over here at 1 if I decrease and increase. Relative min here. Again, I don't know right now if they're absolute or not. We're not going to worry about that at this point. So I also have a relative min at 1, which is 1 f of 1. If I plug 1 into the original function, right, remember f of x was x to the 4th minus 2x squared. So if I plug 1 into the original, 1 to the 4th minus 2 times 1 squared, I get 1 minus 2, which is -1. So 1, -1. Okay? And then where would we have a local max? Well, I would have a local max right here when I increase and then decrease. So it would be at 0, right? If I increase and then decrease, I'm going to have a relative or local max. So at x equals 0, or the point 0, comma, plug it into the original, and it spits out 0. All right, let's go ahead and do the same thing for this one. Let's find our critical numbers where it's increasing, decreasing, relative, min, max, and all that here. So number 1, here's our function, 27. So we're going to find our critical numbers, and I'm going to go ahead and write the function. What's our critical numbers? Here's our function. F of t equals 27t minus t cubed. Let's go ahead and take our derivative. So we got 27 minus 3t squared. Where's the derivative equal to 0 or undefined? Well, we got t being 3 and t being -3. So -3 and 3. That's what we're going to put on. Let's run our first derivative test. Those are our critical numbers, -3 and 3. Notice they're defined in the original function. In order to be critical numbers, they do need to be defined in the original function. We're going to run the first derivative test. So we're going to plug in like f prime of negative 4, something to the left of negative 3. We're going to plug it into f prime of t. F prime of t is 3 times 3 minus t times 3 plus t. And we're going to plug in something to the left. Something to the left of negative 3. And I said negative 4. So we got 3 times 3 minus a negative 4. 3 plus a negative 4. So we got a positive times a positive 7. 3 minus 4 is a negative 1. So it looks like this just ends up being a negative 21. So we're less than 0. The derivative is less than 0, negative. So the original function must be decreasing because all the slopes of the tangent lines are negative to the left of negative 3. Now we're going to throw in something between negative 3 and 3. I like to use 0. Let's use t being 0 on this one. So f prime at 0 would be 3 times 3 minus 0, 3 plus 0. So we got 3 times 3 times 3. So f prime at 0 is definitely positive 27. So the original function must be increasing between negative 3 and 3. Finally, let's throw something in to the right of 3. How about just a 4? F prime at 4. So I got 3 times 3 minus 4 times 3 plus 4. I got 3 times negative 1 times 7. So f prime at 4 is a negative value. So the original function must be decreasing after 3. So let's go ahead and write that down. We are increasing between negative 3 and 3. Right? Hopefully you can see that on the graph. Between negative 3 and 3, the original function is increasing. And we're decreasing in red from negative infinity up until negative 3. And then after 3, we're also decreasing. So 3 to positive infinity. Where's our relative min at? You know, where we decrease and then increase. So we would have a relative min right there, right? I go down and then up. That would be where the bottom of the valley is at negative 3. So the relative min is at t being negative 3, or the point negative 3. And I'd have to plug it into the original. Remember, the original was 27t minus t cubed. So if I plug negative 3 into that, it'll spit out negative 54. So plug it into the original if you need a coordinate. Okay, where would you have a relative max? At the top of a hill, right? So at 3, we would have a relative max at t being 3, or the point 3. Again, plug it into the original function, and this original function spits out 54. Okay. Now, I do want to think about this a little bit with our pre-calculus. If you think about this function here, let me go down here for just a second. F of t is 27t minus t cubed. Let me write it this way: negative t cubed plus 27t. Notice that the original, this original function is odd, but the leading coefficient is negative. So it looks like kind of like negative x cubed. It's going to go up to the left and down to the right. And what's more about this, goes up to the left, down to the right. At negative 3, like it decreases, 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 and then at negative 3 it turns. And it's going to then increase between negative 3 and 3. So it increases, again, I don't know what it looks like, but it increases until it hits right here at 3. And again, I don't know how high or how low this goes, but then it decreases afterwards. So hopefully you can see that, hey, I've got a local minimum right there. I've got a local maximum, but there's no absolute extrema here with this polynomial, this being a cubic. So here we've got x minus 2 times e to the negative 3x, e to the negative 3x. I'm going to go ahead and run this when I find my critical points with the product rule. So here's our function. That's our first one times our second one is e to the negative 3x, right? So product rule, derivative of x minus 2, derivative of the first times the second plus the first derivative of the second. So that would be ln e to the negative 3x. Chain rule, derivative of negative 3x is negative 3. So f prime of x would end up being e to the negative 3x. ln e, of course, is just 1. So I've got, let's see, minus... So I'm going to factor out with this derivative here. Let's factor out e to the negative 3x. So that would leave me with 1 minus 3x minus 2. So I got 1 minus 3x plus 6. In other words, 7 minus 3x. Or if you want to think about it as 7 minus 3x all over e to the 3x, same thing. Here's our derivative, right? Now we want to know, where is this thing equal to 0 or undefined, right? Where would it be equal to 0? Well, where is f prime equals 0? If 7 minus 3x equals 0. In other words, if 3x equals 7 or at 7/3, right? Now, where would this thing be undefined? Where would f prime be undefined? Well, if e to the 3x equals 0. Will e to the 3x ever be 0? No, because if I run the natural log on that, the natural log of 0 does not exist. So this will produce, that e to the 3x will not produce any critical points. So I'm only looking at step 2 on this. When I run this first derivative test, I'm only looking around 7/3 on this. Okay. And so we could throw in some points here to the left of 7/3, like maybe f prime at 1. So I'm going to throw it into 7. Let's leave the f prime of x for a minute. So I got 7 minus 3x over e to the 3x. So f prime at 1 would be 7 minus 3 times 1 over e to the 3 times 1. So I got 7 minus, I got 4 over e to the 3rd. Now remember, e is 2.718, right? So this is a positive over another positive. So this will end up being a positive value. So the original function must be increasing up until 7/3. Let's go ahead and test something over here after 7/3, like maybe 3, right? 7/3 is like 2 1/3, so let me throw in 3. 7 minus 3 times 3 over e to the 3 times 3. So I got 7 minus 9. I got a negative on the top. E to the 9th is a positive value on the bottom. So I've got a negative, over a positive. So that ends up being a function that is decreasing, right? So let's go ahead and note these. Our critical number here was simply 7/3. We were increasing from negative infinity up until 7/3. We're decreasing after 7/3. We have relative min. We don't have a relative min because it doesn't decrease then increase, so not applicable. We do have a relative max at 7/3, right? Top of a hill. So at 7/3, or if you want to plug it in, the point would be 7/3 plug that in. 7/3 minus 2 times e to the negative 3 times 7/3. I'm plugging this into the original function. That looks like that ends up being 1/3 e to the 7th if you plug that into the original function. Find the critical numbers of the square root of 9 minus x squared all over x squared. So let's start out, find our critical points. So here's our original function, square root of 9 minus x squared. I'm going to write that as 9 minus x squared to the 1/2 all over x squared. Let's go ahead and run the quotient rule. So derivative of the top, chain rule, times the bottom, minus the top, derivative of the bottom, all over bottom squared. And so this derivative ends up being, let's see, that would be, the 2's cancel right there. So I got a negative x cubed over the square root of 9 minus x squared, right? 9 minus x squared is negative 1/2. And then I've got minus 2x squared of 9 minus x squared. And this is all over that x to the 4th there. So I'm going to go ahead and this is over 1. Let's get a common denominator. Let's give this the square root of 9 minus x squared, square root of 9 minus x squared on this. And so our derivative will end up being negative x cubed minus 2x times just a regular old 9 minus x squared, since we had two radicals being multiplied, all over x to the 4th, square root of 9 minus x squared. So this derivative ends up being negative x cubed minus 18x plus 2x cubed over x to the 4th square root of 9 minus x squared. 2x cubed minus x cubed is just an x cubed. Let's take an x out of the top. So one of those x's will cancel, leave us x to the 3rd. So I got x squared minus 18 over x to the 3rd square root of 9 minus x squared. There's our derivative, right? And we're wondering, where is this thing equal to 0? Right? Let's answer that first. Where is the derivative equals 0? Well, if x squared minus 18 equals 0. So add 18, square root. So I got plus or minus the square root of 18, plus or minus the square root of 18. In other words, plus or minus, that would be 3 root 2. That's where the derivative is 0. Where's the derivative undefined? Well, I have x cubed and I have, if x cubed is 0, or the square root of 9 minus x squared equals 0, right? Because we can't divide by 0. So 0 would be a problem. Let me square both sides of this. 9 minus x squared equals 0 squared. Let me add x squared to both sides. And then let me square root both sides, plus or minus 3 on that. Okay. Now, note before I want to make sure these are in my, hold on, let's start putting our first derivative test here. Okay, so I have plus and minus 3 on this. Now, before I jump to any conclusions, 0, and then we have 3 root 2, negative 3 root 2. Okay. Now, to be a critical point, though, it must be defined in the original function. It must be defined in the original function. So let's think about the original function here for a minute. I have f of x. Sorry, I kind of ran out of room, you guys. Here's my original function. Okay, what's my domain of this thing? What's my domain? Well, I can only take the square root of a positive number. So I know 9 minus x squared has to be greater than or equal to 0. Let me add x squared to both sides and write it this way: x squared less than or equal to 9. If I square root both sides, now notice I have a less than or equal to. So technically that's the absolute value of x is less than or equal to 3. So in other words, I have to be between -3 and +3. The original function has got to be between -3 and +3. And x cannot be 0 either. So I'm cutting this off. That means I cannot even look at the 3 root 2 and the -3 root 2, right? That's like 4 point something. That's outside my domain. So I'm going to erase those completely. I can't look outside 3 and +3. I'm stuck. Oops, how am I going to do this? I'm stuck between there. No and no. Nothing outside there. I'm stuck between -3 and +3 for my domain. And what's more is 0 is not even defined. So it's not a critical point. Okay? Now, I'm going to still test around -3 and +3. Let me erase this stuff, you guys, our domain stuff here. I'm sorry, I'm going to test around 0, but just note that it's not defined in the original function. So if it's not defined in the original function, even if it's like increasing or whatever, I'm not going to have a point at which I have a local max or anything because I'm not defined there. Okay. So my only critical numbers here are -3 and 3. 0 does not count because 0 is not defined in the original, but we're still going to test around it. Again, I need to emphasize that. Not defined, so not critical point, but test around 0. You still want to test around 0. So let's go ahead and throw in something to the left of 0. So let's plug in f prime of -1. So I got -1 squared minus 18 over -1 cubed times the square root of 9 minus -1 squared. So I got 1 minus 18. I got a negative on the top. I got a -1 right here. And then I've got a square root of a positive number right there. So I got a negative over a negative is a positive value. So I know the original function must be increasing up until 0. Now let's throw in like 1, f prime of 1. So I got 1 squared minus 18. So I got a negative on the top. I got a 1 cubed times the square root of 9 minus 1 squared. I got a positive on the bottom. I got a negative over a positive times a positive. So negative over a positive is a negative. So f prime of 1 is negative. So the original function must be decreasing from 0 to 3. We were increasing from -3 up until 0. Okay. Now, relative min or max on this, we do not have a relative max here at least at 0 because it's not defined there, right? Because we have a vertical asymptote at 0, right? It's not defined in the original function. Okay. Now the question is, because this domain is restricted to -3 to 0, then there's a break, and then 0 to 3, right? I really should check my endpoints, right? So I really should check what's the value at -3 and what's the value at 3. Or if I plug those into my original, so my original function was the square root f of x is the square root of 9 minus x squared over x squared. So if I throw in -3, see I get square root of 0 over 9, so I get 0. And then at 3, I get 0, right? So the function hits -3, 0, it hits 3, 0. It's not defined. There's a vertical asymptote at 0, but I increase. And I don't know what the increasing looks like, but I'm increasing. This function is increasing, and then we're decreasing, right? So no relative max, but we do have minimums. In fact, they're not only relative minimums, they're actually absolute minimums. And they occur at the endpoints. They're actually more specifically absolute minimums. All right, we've got a trig function here, f of theta. We're going to have to use the sine cosine product rule. So let's go ahead and take this derivative of the sine, derivative of the first times the second plus the first, derivative of the second, derivative of the cosine is negative sine. And so we've got cosine squared minus sine squared theta. That's our f prime of theta. Now we're trying to figure out where this is equal to 0. So I'm just going to go ahead and make a substitution. Let's put this all into cosine. So remember, sine squared plus cosine squared is 1, right? So sine squared would be the same as 1 minus cosine squared. So I'm going to make that substitution so I can make this solvable. Replace sine squared with 1 minus cosine squared. And so our derivative ends up being cosine squared plus cosine squared. I got 2 of these cosine squareds minus 1. Right? And so set that equal to 0. So I'm going to add 1, divide by 2, divide by 2. I got cosine squared equals a half. Square root, square root. So the cosine of theta is plus or minus square root of 1 over square root of 2. So cosine theta is plus or minus root 2 over 2. Right? And notice they did ask for a restricted domain. They just want you to look at the intervals on which it's increasing or decreasing only between 0 and pi. So when I'm going back to this and naming this, like the cosine of theta is root 2 over 2. Right? Where is the cosine of theta root 2 over 2? You know, if I'm looking on my unit circle, I'm like, oh, pi fourths, the cosine is root 2 over 2, right? And of course, negative pi fourths, right? But that's not, it's outside. We're only looking between, it was 0 to pi, right? So that would be our other one. Pi fourths, 7 pi fourths. Again, that's outside our domain, so we're not going to look there. How about where's the cosine of theta negative root 2 over 2? Right, where's it over here? negative root 2 over 2. 3 pi fourths, right? Theta would be 3 pi fourths. And of course, the next one would be 5 pi fourths, but again, that's outside. We're only looking between 0 and pi here. All right, so now let's go ahead and run our first derivative test. So we've got pi fourths, we got 3 pi fourths, but remember, this has been artificially cut off between 0 and pi, right, between 0 and pi. So I do want to think about my endpoints on this as well, okay? Let's plug in something before pi fourths, like maybe pi 6. So f prime at pi 6. So I've got, throw that in. I could throw it into either 2 cosine squared of pi 6 minus 1. I'll probably throw it into that one. But you could also throw it into cosine squared minus sine squared, either one of those. Right? So f prime at pi 6, this will end up being positive, so the original function must increase. I'm going to throw in something between pi fourths and 3 pi fourths. How about pi thirds? F prime at pi thirds would be between pi fourths and 3 pi fourths, and that'll end up being negative. Again, throw it into the derivative. Now I'm going to pick something between 3 pi fourths and pi. So how about 5 pi 6? I'll plug in 5 pi 6. This ends up being positive as well, so it increases. Okay, so let's go ahead and name our critical numbers. We're only pi fourths and 3 pi fourths because we're only looking between 0 and pi. We're increasing from 0 because they cut it off at 0, 0 up until pi fourths, and then we're also increasing from 3 pi fourths up to pi. We're decreasing between pi fourths and 3 pi fourths. And then finally, we have a relative max at that pi fourths. Plug this into the original function, which is sine of pi cosine of pi. And that'll end up being root 2 over 2 times root 2 over 2, which is 2 fourths or 1/2. Plug that into the original function. And then relative min would be at that 3 pi fourths. Right? I decrease and then I increase. So I plug that into my original function and I get negative 1/2 on that. Here we've got one more algebraic function. We got 3x to the 2/3 times x minus 5/2. Let's find our critical points of this function. You know, I'd probably just distribute that through 3x 2/3 plus 1 would be 5/3 minus 15/2 x to the 2/3, and then I would go ahead and take the derivative. Power rule. So I got 15/3. I got 5x to the 5/3 minus 1. So 5/3 minus 3/3, 2/3 minus, let's see, constant stays there. I'd have 2/3 x to the 2/3 minus 1, so negative 1/3. So we got 5x to the 2/3 minus 30 over 6, so minus 5 x to the negative 1/3, so over to the third root of x. So where's this thing undefined? Let's answer that first. Where's this thing undefined? Well, I can't divide by 0, so wherever this is 0, that would be a 0. So we're undefined at 0. And that's a critical number as long as I can plug it into the original function. Can I throw a 0 in here and it'll spit a number out, a value out? Yes, it will. So x being 0 is defined in the original function, so it is a critical number. Now, where is f prime equal to 0? So where does 0 equal 5x to the 2/3 minus 5 over x to the 1/3? Well, this is over 1. Let's get a common denominator, x to the 1/3, x to the 1/3. And so 0 equals 5x minus 5 over x to the 1/3. So it'll equal to 0 whenever 5x minus 5 equals 0 or x equals 1. Make sure 1 is defined in the original function. If I plug a 1 in, is it defined? Yes, it is. No problems. So both 1 and 0 are critical numbers. 0 and 1. So now I'm going to go to my first derivative test. I'm going to throw on 0 and 1. And I'm going to plug in points like -1, f prime of -1. So I got 5. I'm going to plug it into this derivative here. 5 times -1 to the 2/3 minus 5 over the 3rd root of -1. So I got 5. Let me write this as, well, -1 to the 2/3. You can just use your calculator if you want, or that's the 3rd root of -1 squared, right? So the 3rd root of -1 is -1, and -1 squared is +1. So that'll be a 1 minus 5 over 3rd root of -1, which is -1. So I got a 5 plus a 5, which is a +10. So this is increasing. Let's throw in something between 0 and 1. I'm going to be strategic because I have 3rd roots on this, so I'm going to throw in like 1/8. So I got 5 times 1/8 to the 2/3 minus 5 over the 3rd root of 1/8. And so I got 5 times the 3rd root of 1/8, that's 1/2, and 1/2 squared is 1/4. 3rd root of 1/8 is 1/2. So I got 5/4 minus 10. So -35 over 4. The point is that is negative. So then we are decreasing between 0 and 1. And finally, let's throw in like f prime of 8. If you throw in f prime of 8, you'll get that thing being positive. Okay, so let's fill this out. We're increasing between negative infinity and 0. And then we're increasing again after 1. Increasing again after 1. We're decreasing between 0 and 1 on that interval between 0 and 1. And we have a relative min at x being 1, or the point 1. Plug it into the original function. That'll spit out -9/2. Again, plug it into the original function there. You do have a relative max at an x value of 0, or the point 0, 0. That'll spit out 0 on that. Well, thanks so much for taking notes on the first derivative test, and we'll see you next time.